Welcome to this new lecture in our class Advanced Algorithms and Optimization. Today we will discuss about branch and bound, and we will apply this technique again on the knapsack problem to explain all the details of this new approach for solving discrete optimization problems. So if you remember, our knapsack problem was with the following form. So we wanted to maximize the value of the selected item. So each item can be selected. In that case, you put the variable to 1 or is not selected. And of course, you have this capacity constraint in your knapsack, which is that you can select a weight of at most 9, given, for instance, the weight for each items, which are 4, 6, and 4 in this case. And so one possible enumeration to enumerate all the possible solutions was to explore with the brute force approach all the possible assignment of these decision variables. And you can see that there are 8 possible ways of enumerating them, and you can implement that using the exploration of the search tree like that, in which at each level you would decide to select or not to select each item. So the level 1 is for item 1, the level 2 here is for item 2, and the level 3 is for item 3. And so if you go completely to the left here, you would take 1, 1, 1 for the variable x1, x2, x3, which means that you select all of them. Okay? And so the important question, if you want to shift a little bit the exponential time, so if you remember, this was my graphic, so you've got the exponential behavior in which you've got the time to solve it, and this is the size. If you want to be able to shift a little bit further the exponential to the right, you need to prune a little bit this search tree. And so to prune this search tree, one easy way to do it is by using upper bounding procedure to cut a little bit the branches of this search tree, which means, for instance, cutting large part of the search tree that you don't need to explore. The way it works for an optimization problem like this one, so if you want to maximize an objective function like this one, is that first you need to assume that you have a feasible solution with a given objective value, which means, for instance, which is this one. This is a feasible objective value that you have, that you can, for instance, obtain with a greedy algorithm. Okay, you've got an heuristic, you implement a greedy strategy, and you've got at least one feasible solution. Of course, it's not the best optimal solution. You don't know if it's the best one. You want to prove it or possibly find another better one, but at least you've got that one. And you can also assume that it's quite easy to decompose your problem in two, okay, in two sub-problems like P1 and P2. Okay, you would split the problem in two here. And we also assume that we have an upper bounding procedure, which means a procedure that will be very optimistic. And it gives me an upper bound on the possible objective function for a given problem P. Okay? What you can immediately see if you assemble all these pieces together is that if the upper bound on P1 is worse, so is less good than the best solution that you have found so far, you can discard the exploration of P1, okay? It means that P1, you don't even need to explore it, okay? You don't need to explore it because in the best, if you are really optimistic, it means that you would be able to reach this upper bound, okay? Of course, this is an upper bound, so maybe that the best solution there is even lower than this. But even if you're optimistic, you are less good than what you have already found. So it means that you don't need to explore that part of the search tree, okay? And you can discard the exploration of P1. Of course, what is interesting here is that the upper bounding procedure should be very cheap to compute, okay? It should obviously be cheaper to compute than finding the best feasible solution in P1. Okay, we assume that it is cheap in terms of computation to obtain this upper bound. That's the idea of branch and bound, and in the next video I will see how we can instantiate this framework for the knapsack problem.